sometimes we don't have just the right ingredients, right? In fact, usually we don't. When you're making pizza or pancakes or any recipe, do you ever use up all the ingredients exactly? When was the last time that happened? Like never, right? There's usually one ingredient that you run out of, but you've got lots of random amounts of the others left over. And that happens in chemical reactions too. But let's look at pizza again. So if we have 4 crusts and 10 cups of cheese and 15 ounces of tomato sauce, how many pizzas can we make? Now, I don't know about you, but just looking at those amounts, it's not really jumping out at me what the answer is. So how would you figure it out? Well, you'd think, well, how many pizzas can I make from 4 crusts? Well, that was pretty easy. 4, right? 4 crusts times 1 pizza per crust means we could make 4 pizzas if we used all the crusts. 10 cups of cheese. Well, 10 cups of cheese, you get 1 pizza for 2 cups of cheese, so you could make 5 pizzas. Could we actually make 5 pizzas, though? Do we have enough crusts? No. 15 ounces of tomato sauce. 15 ounces, 1 pizza takes 5 ounces, so the tomato sauce will only make 3 pizzas. So we're making pizzas. We make 1 pizza, we make 2 pizzas, we make 3 pizzas. What happens? We ran out of tomato sauce. And we're not going to improvise and make one with pesto or something. That's not we're not improvising, okay? My husband would do that, but that's not what we're doing. We are following the rules. Pretend you were working for me and Ed's or something, and you'd get fired if you started shooting out pizzas without sauce on them, right? So we can only make 3 pizzas. The tomato sauce is what's limiting how much product we can make. And so we call that the limiting reactant. These are reactants: the crust, the sauce, the cheese. The one that runs out first is our limiting reactant. The way we figure that out is you take each ingredient and you calculate the number or amount of product that you could make. Then you look at these and you pick the smallest one. You do not add them all together. Sometimes people get creative. I don't know what they're thinking. Sometimes I think they're not thinking. But don't do that. Just find the smallest one. It's just easy that way. Oh, they're going to have us look at pictures. I think we can figure that one out. But look, there's the pictures. They don't look all that great. So the tomato sauce is the limiting reactant. The maximum number of pizzas we can make is called the theoretical yield. So that's the most we could make. And it's theoretical because sometimes stuff happens when you're cooking, right? You know, the cat jumps up on the counter and walks through the pizza. It could happen. Then you have to throw that one out. You could have made 3 pizzas, but the cat ruined one, and so you only got 2. Theoretical yield is everything works the way it's supposed to. That's what you get. So in our chemical reactions, the same thing's going to happen. One of the reactants is probably going to get used up. When it gets used up, it stops. The reactants that are not completely consumed are called excess reactants because there's extra of them. The amount of product that we actually get is called the actual yield. So perhaps while making pizzas, we burn one or we drop one on the floor, so we only make 2 pizzas. Then 2 pizzas is the actual yield. 3 was the theoretical yield, but we screwed up. We find percent yield to be useful in measuring how well we did or how efficient the reaction is. Percent is, and it's not really given here. I gave all kinds of other crazy stuff in this. Percent yield equals the actual yield divided by the theoretical yield. That's not an E. That's an E. Theoretical times 100. The part over the whole. How much you actually made out of how much you could theoretically make. So the most you can get there is 100%, right? If everything works perfectly, you can get 100%, that'd be awesome. That's a summary. Good grief. I'm just finding these slides very tedious tonight. There's theoretical yield, actual yield, percent yield. Great slides to go back to and look at. They just spell everything out, but how many times do we need it spelled out? So applying this to a chemical reaction. Here's looking at the combustion of methane. Combustion always involves oxygen and produces carbon dioxide and water. And so here we've got the methane, and it's reacting with 2 oxygen molecules. It produces 1 carbon dioxide molecule and 2 water molecules, right? Yay. We could also multiply all of this by 12 and say a dozen of these plus 2 dozen gives us 1 dozen and 2 dozen. Or we could multiply by a mole and say that 1 mole to 2 moles gives us 1 mole and 2 moles. If we stay with the number of molecules, what if we have 5 molecules of CH4 and 8 molecules of oxygen? What's the limiting reactant? Well, first we calculate the number of carbon dioxide molecules that could be made from 5 methane molecules. From this reaction, we can get 1 CO2 from each methane. So here's 1 CO2 per 1 methane. The units work out, we get 5 CO2 molecules. Then we look at the other reactant, the oxygen. Oxygen, it's 1 CO2 for every 2 oxygens. So 8 oxygens will get us 4 CO2 molecules. 4 is smaller than 5. So this is our theoretical yield, and this is our limiting reactant, the one that gives you the smallest yield. So this is the way your book presents it, and if you want to do it that way, that's fine. I'm not a big fan of it, but it works. Usually, though, we're dealing with masses, right? And we have a mass of the reactants we're starting with. We want to find out what the mass of the product is. So your book is saying to find moles of product and identify which one is smaller, and then take that one and calculate the mass of the product. I think it's more straightforward just to go to mass of product for both of them, and then see which is smaller, and you're done. It's not really any more work. In fact, it's less writing down of stuff. So that's what I'm going to show you. So here's an example. A fuel mixture used in the early days of rocketry consisted of 2 liquids, hydrazine and dinitrogen tetroxide, which ignite on contact to form nitrogen gas and water vapor. How many grams of nitrogen gas form when 1 times 10 to the 2 grams of hydrazine and 2 times 10 to the 2 grams of dinitrogen tetroxide are mixed? Doesn't this look fun? No? Okay. Well, we're going to do it anyway. We need a reaction. They didn't give us one. They gave us the formulas for hydrazine and dinitrogen tetroxide because they were kind. We could figure this one out. The hydrazine, we couldn't. But these are our reactants. So I'm going to do these up here. So N2H4 plus N2O4. I'm going to leave a space there because I may need a coefficient. They ignite to form nitrogen gas and water vapor. What is the formula for nitrogen gas? N2. Nitrogen is one of the diatomic elements. Here it is by itself, and so it's N2. And then water vapor is H2O. So we've got our reactants and our products. And then we need to balance this equation. Yeah, this is a fun one. What element would you like to start with? Nitrogen? Okay, let's start with nitrogen. So we've got 2 and 2 is 4, and on the right side we only have 2. So if we put a 2 here, that'll take care of our nitrogens, right? And then we've got oxygen and hydrogen. Let's do oxygen. So over here we've got 4 oxygens, and here we've got 1. So if we put a 4 there, we're going to have 4 oxygens. And that didn't do anything to the nitrogens, so they're still okay. Let's look at the hydrogens. 8 here and only 4 there. Well, we'll have to put a 2 in front of it to fix the hydrogens. Now we messed up the nitrogens, right? So let's erase this, because that's not going to work anymore. We have 2 times 2 is 4, plus 2 is 6. And so if we put a 3 here, then we should be good. Okay? Balanced chemical equation. We can use this balanced chemical equation to organize this information that they gave us. So they gave us a mass of hydrazine. So I'm going to write the mass of hydrazine underneath hydrazine in the equation. I've got 1.00 times 10 to the 2 grams of that. And the N2O4, I have 2.00 times 10 to the 2 grams. And what do they want me to find? Grams of nitrogen gas, right? How many grams of that? So we have masses for 2 reactants, and they're asking us for a mass of product. When they give you masses of 2 reactants, you should assume that it's a limiting reactant problem. So we're going to take this one and calculate mass of nitrogen. We're going to take this one and calculate mass of nitrogen. And they will both use grams to moles to moles to grams. So we'll have 2 equations. We'll get 2 answers. The smaller one is the right one, because that's how much you've made when you run out of one of the reactants. Okay, so let's start with the hydrazine. 1.00 times 10 to the 2 grams N2H4. Times, we're going grams to moles, so moles of that guy. And then we're going to moles of the other guy. I'm writing too big. Oh well. And then 2 grams of that guy. We put the units in the bottom to cancel out. If dimensional analysis is still a bit of a mystery to you, today would be a good day to get it cleared up. It's not going away. Questions about the units? Where do we get the coefficients, the numbers for this middle term? From the balanced chemical equation. In front of N2H4 is the number 2, so that comes down here. In front of N2 is a 3. Really, what can be easier? You find the compound, you look at the number in front of it, you write it in the equation. That's why I always do that one first. It's just nice. First term, last term are molar masses. So we need the molar mass of hydrazine. 2 times 14.01 grams plus 4 times 1.008 grams. 35.052 grams equals 1 mole, or grams per mole. I prefer not to round those molar masses here unless they get really, really long, but they rarely do. That little 2 isn't hurting anybody, and we'll get the right number of significant figures back in the end. It's going to be 3. Mass of nitrogen is 2 times 14.01, which is 28.02 grams per mole, or grams equals 1 mole. So we put that in here, and I didn't leave enough room. 1 EE2 divided by 35.052 times 3.
Yeah, it's 32.052.
Oh, thank you. I should have started counting the number of blunders like this I've made today. I think I'm up to 7. I'm not sure. Thank you. That makes a difference. It's easy to do, and I see it on students' papers all the time. It's fine if you aren't actually calculating the amount of medicine someone needs. Okay, so if I round this to 3 significant figures, I get 131 grams of nitrogen gas. This will be a final answer, and we started with 3 sig figs. Everything in here had 4 or more. These are exact numbers, so we don't have to worry about those. And then we're going to do a very similar calculation for the other reactant. 2.00 times 10 to the 2 grams of N2O4. And so this will be moles of N2O4 per grams N2O4. So those guys cancel out. And then we'll get moles of N2 for moles of N2O4, and those guys will cancel out. And then we'll get grams of N2 per mole of N2, and those guys will cancel out. Now, this is one of the reasons it's not that much, it's not really even any extra work to go ahead and calculate the mass of product for both. This last term is the same for both of them. So it's really no extra work at all, 28.02. The guy in the middle, chemical equation, 3 and 1. Molar mass of N2O4. Okay, way to calculate that. 2 times 14.01 plus 4 times 16. $92.02. And this one comes out to 183 grams of nitrogen. So how much can we make? 131. Because as we're going along, we're making 100 grams, 120, 130, 131 grams, bang, stops. We ran out of one of the reactants. Nothing else can happen. Any questions?